but let's move on to the next speaker, who is Alexandra Reste from Stockholm, who's telling us about spatially resolved comparison of Lyman alpha and atomic hydrogen emission in low redshift, high redshift analog galaxies. You are here, right, Alexandra? Yes.
Hey, yes, can you hear me?
Yes, indeed. And I will start the time now.
Okay. Can you see my screen?
We can. But now I think you muted yourself.
Can you hear me again?
Yes, now we can hear you.
Okay, so I'm Alexandra Reste. I'm a PhD student at Stockholm University, and I'm going to tell you about a work that I did with the last team on the first spatially resolved comparison of Lyman alpha and 21 centimeter H1 emission in galaxies that are analog to the one at high redshift. So the talk is going to go like this. I'm going to start with a short introduction, just stating the questions that motivated this study. I will show a bit more about the sample. I'll present the H1 observation and the multi-wavelength analysis showing the Lyman alpha and the other components of the interstellar medium. And I will finish with a brief conclusion. So Lyman alpha is a key probe of galaxies at high redshift. And it's essentially, I'm not sure everyone is familiar with it, so I'll just give a bit more of the basic. It's the transition between the first excited state of the hydrogen atom and the ground state. And it's a resonant line, which means that it's captured by the hydrogen, and it's also absorbed by dust. So the photon transfer in the interstellar medium should be mainly impacted by the dust and the H1 content, but also distribution. And so in order to use Lyman alpha at galaxies in the epoch of reionization, we need to understand how Lyman alpha transfer proceeds in galaxies and how the multi-phase interstellar medium impacts it. So the thing is that we can't really get good result of the observation of H1 and of the 21 centimeter emission, which is the best tracer of the H1 at high redshift. So the observations of local galaxies are the only way to get a precise view of how the Lyman emission is impacted by different phases of the ISM. And so that's exactly what the Lyman alpha reference sample has been created. So the LAS and ELAS sample are made of 42 nearby, and when I say nearby, it's very nearby for people in the audience at redshift of 0.03. And they're star-forming galaxies, and they were selected on H-Alpha equivalent width and FUV luminosity criteria to resemble Lyman break galaxies. And you can see on the bottom the BPT diagram on the left and the main sequence on the right, with the galaxies in the sample that are overlaid. Now, we didn't use the full LAS sample to do this study because H1 observations are quite hard to get at the resolutions we wanted. So we observed two galaxies, which are LAS 8 and ELAS 1, or NGC 6090. They are quite massive. They have stellar masses around 10 to the 11 solar masses and quite metallic as well. So they're very different from what you would see at high redshift. And you can see some nice HST color images on the bottom of those two galaxies. And the Lyman alpha is the fuzzy blue that you can see there. And so these galaxies were selected mainly for their very high H1 luminosity, which would allow us to do those high angular resolution observations. And now if you want to compare it to the diagram I showed you before, this is the position of the two galaxies on the main sequence. And so we went and got some very large array observations of the 21 centimeter line for those two galaxies. And so we observed the two galaxies using all the different array configurations from the more compact, that is more sensitive to large scale emission, to the more extended baselines, which have a good angular resolution. And we got 50-hour observations per galaxy. And with that, we were able to make a final H1 data queue by combining data from all the array reaching a 3 arcsecond resolution in H1, which is roughly 2 kiloparsec physical resolution at those redshift. And this is what we see. So on the top panel, you can see last 8 H1 moment map, and on the bottom panel, this is last one. From the left to the right, you have the column density map, the weighted velocity map in the reference frame, and the standard deviation map for the velocity. And we get a mass of roughly 10 to the 10 solar masses for the H1 in both systems. And so if you want to compare to the HST image that I showed previously, this is the HST field, which is 40 arcsecond that is overlaid on the images. And the images that I showed in previous slide is really at the center of that. So that really shows how extended the H1 is. And on both, in both those galaxies, we can actually see signs of interaction. In last 8, you have a small companion galaxies that is to the west, the southwest of the galaxy. And the last one, you have very extended tidal tails of H1. Now, the most interesting part, I guess, is so the comparison with different phases of the ISM. So if we look at the H alpha and the H1, this is the figure on the left, where you can see the moment map that I showed previously with the H alpha emission from Muse overlaid. And you can see that there are there is star formation going on along the spiral arm, but also, and most importantly, very strong star formation in the center. And to the right, you have the extinction map that is computed using the H alpha over H beta ratio. And essentially, the lighter colors show you lower dust content, while the darker colors show you more dust in the galaxy. And so there is really this divide in the galaxy between the west and the east, and we'll see that's quite important. So the western part of the galaxy has much less dust than the rest of it. Now, if we look at the Lyman alpha and the H1, and this is the first time we can see that at those resolutions, we see that the Lyman alpha essentially is located to the west. This is also the place where there is lower dust extinction, so it's quite interesting. And it's nearby the more high column density H1 contours, but it's still not overlapping with the high H1 column density. And then if you look to the right, this is Lyman alpha overlapped on the moment 1 map, and it is coincident with the blue shifted side of the H1 disk. Now this is interesting, but I think the more interesting part is the 3D analysis, because we can do that with an H1 cube. And so the top panel shows the Lyman alpha versus the H1 spectrum. Lyman alpha is the very dark blue line, and H1 is the lighter blue line. And they're both extracted in the same small 3 arcsecond aperture that is there. And what you can see is that there is a redshift of the Lyman alpha line and a blue shift of the H1 compared to 0 velocity, which could explain why Lyman alpha photons can escape easily in the galaxy. And on the bottom panel, you have another way to see that, is to say the H1 channel maps overlapped on the H1 image. And so from left, you go to the blue shifted side to the more red shifted side. And what you can see is that really when you look at the most red shifted part of the H1 disk, you don't have H1 in front of the Lyman alpha image. So that could really explain why it's easier for the Lyman alpha to escape there. Now, if you look at what happens in the other galaxy, in ELAS one, this is the H alpha from PMAS. So we didn't have Muse data for ELAS one because it's a bit too up north in the sky. So we get a bit less resolution than the Muse, but essentially the star forming sites are coincidence with lower column density H1 regions. And if you look at the Lyman alpha, it's essentially at the same position as the H alpha emission. And in that case, we also see that the Lyman alpha is also on the blue side, although the moment 1 map is a bit more noisy because we have less signal to noise ratio with the last one in the H1. looking at the 3D picture of it, this is the same as I showed before for last 8. You have the 2 spectra compared. And here what we can see is that there is basically no H1 to the sensitivities we reach with that cube in the aperture. And so that is basically saying that there is lower column density H1 in front of the Lyman-a emission. And again, you have the channel map that shows really that you don't have much H1 in front of the Lyman-a there, at least to the detection limit. And so what are the ISM conditions? Okay. So the ISM conditions that seem to enable Lyman-a escape in last 8 are the redshift of the Lyman emission while the H1 gas is blue shifted. There is also probably some role of the lower dust content that is not destroying the Lyman-a on the western side of the galaxy. And there could be a link to past interaction and accretion of low metallicity neutral gas that enable that scenario to take place. Now for ELAS1, we seem to have lower column density gas on the line of sight and possibly some redshift of the Lyman-a emission compared to the gas seen by where the Lyman-a is located on the moment map of the H1. And so to conclude, this is the first result comparison of Lyman-a and 21 centimeter H1 emission. We're still analyzing the results, but we have found some points that could possibly explain why Lyman-a is escaping where it is escaping. And although those galaxies are a bit different from what we see in the high redshift universe, physics is still the same. And so obtaining this type of comparison is a step to determine the intrinsic Lyman-a spectra from galaxy. And yeah, the next step will be to get more high resolution data because those 2 galaxies are quite peculiar and it's only 2 data points. So that would be really interesting to see what happens in the galaxies that are in other places in the parameter space. And we're also going to analyze the low angular resolution data in H1 for the ELAS sample and to have an idea of how the global H1 properties impact Lyman-a in all 42 galaxies. And yeah, thank you for your attention and the opportunity.
Better data is always the next step, isn't it? Thanks a lot, Alexandra. You're muted again, and you will need your voice to answer the question that I'll now read to you from Casper, asking, from the low redshift Lyman-a H1 21 centimeter connection, is it possible to predict the H1 content of high redshift galaxies based on Lyman-a emission and how it scales and interacts with H1?
Okay, so for the first part of the question, I think we're really not there yet. That is a goal that would be great if we could just look at the Lyman-a line at high redshift and say, oh, the interstellar medium, in particular the H1 gas is like that. But it's a very complex picture. And there is, when you look at high redshift, of course, there is the CGM as Florian showed in her presentation. There is the IGM that start to participate in this as well. So it's really not straightforward to do this. But that would be great. And the second part of the question, I'm not sure I got it.
So predicting how Lyman-a scales with H1. Would that be possible?
Yeah, so that would be great. So we're going to analyze the global H1 properties such as mass, the global mass, eventually a bit of kinematics as well in the next part of the project. But it's not something that we can do yet.
Okay. If you're so fast at answering questions, you might even be able to answer this one from Ilsang Yun. Why is Lyman-a so compact compared to the H1? You might think that it was extended because of scattering in the halo.
Yeah, I think that depends on. It's actually quite extended, but I think the H1 is always more extended. And then the thing is that if it's scattered in the halo, it's going to be a bit fainter as well. So you might not see it very well. You might need more sensitive observations to be able to really see a Lyman-a halo that would be that faint.
Yeah, all right, makes sense. Thanks again, Alexandra. It's a very nice talk. Very nice work, I think.